So I'm going to be solving the coin change problem, medium Leetcode problem. So you're given an integer array coins representing coins of different denominations and an integer amount representing a total amount of money. Return the fewest number of coins that you need to make up that amount. If it can't be made up by any combination, return -1. So you see these sorts of minimax problems and you immediately think dynamic programming. And rightfully so. If we were to do this recursively, by going through all the coins multiple times, we'd be recalculating things a lot, and we'd have a time complexity in the order of exponential amounts, and we don't want that. So we can do dynamic programming, which reduces it to a sort of linear time scale, time complexity, at the expense of some base complexity that we need, because we're probably going to need some sort of auxiliary memory or data structure in order to store the solutions. You can do it either recursively with memoization or iteratively with tabulation. So either way works. I'm going to be doing it iteratively with tabulation. And so the optimal substructure of the problem is that the amount of money to make 11 cents, for instance, or 11p, would be the minimum amount of coins to make 5p plus 5p plus 1. Obviously, the minimum amount of coins that we need to make 5p would be just taking one 5p coin, so as opposed to taking a bunch of 1p coins. So the minimum amount of this will be made up of the minimum amount to make the smaller coins underneath it, which makes a lot of sense. So we can just write a recursive relation to establish this. So let's say f of s, where f returns the minimum amount of coins to make s coins. Now this is going to be equal to the for all coins Okay, so I've written a bit, but to explain what I've done, what we need to do to make s number of coins, to make s cents rather, would be to go through all the coins we have in our denomination. We then check, okay, is this the optimum amount of coin? We take that coin. So let's say I want to make 20p. I want to make 20p with the least amount of coins. Then I take a 10p, for instance. For example, obviously the best way would be to take a 20p coin if that denomination exists. We take a 10p coin. If I took a 10p coin, the problem no longer becomes finding the least coins for 20. The problem becomes the least coins for 20 minus 10, which is 10. And then we add 1 because obviously we've just taken a coin. So we're going to go through all our coins and see what's the smallest amount, what's the smallest coin number to make this much. So then our base case becomes so the minimum amount of coins to make 0 coins or 0 cents is 0. And if we can't find a good combo, return -1. So if we can't find anything that works, then just return -1. So we can actually begin coding with this in mind. So int n is equal to coins.length, and then we can say okay, so to explain what I've just done, I've just made a variable to make my life easy, and then I've made this array. This is the bread and butter of the problem, the sort of meat of the problem, if you will. This effectively tracks the optimum amount of coins that I need to make however many cents. So dp of 5 would be what's the least amount of coins to make 5 cents. dp10 is the least amount of coins to make 10 cents. And we're building up these solutions, these smaller solutions, in order to calculate what dp of amount is, which is the best way to make this amount of money, which is our target. We can do this by establishing our base case and building it up. Why I've done this is because we're trying to find a minimum problem. We want to populate our array. By default, Java instantiates the array values to be 0, which is not good. This will break our solution down because 0 is obviously already the minimum amount of anything. which means that we can't find anything that's potentially smaller. So we want to have a number like 100 so that we can compare it to and have that as our starter value. If you were thinking about it in the reverse case, if you're trying to find the maximum, you want to start with the minimum amount of coins so that you can begin comparing. So this is just a large number that we can check. Now, obviously, if DP amount is equal to 100 at the end of this, then we know that we haven't found a good combination, so that we can just return -1. But if DP amount isn't 100, then we know that we found something, so we can return DP amount. That's just a quick explanation of that. So now we want to go through all of the cent values up to amount and build up the minimum amount of coins to make each cent value. So we do it by just doing a iteration like this. So then we want to go through all our coins and check which coin we can use. So we're going to go through all our coins now. Great. So we're going to go through all our coins just to find out which ones we can use. We're going to check each coin, see if we can take that. Obviously, if I have a 10p coin, I can't use that to make 5p. So then we have to quickly check if the coin that we're using is actually less than what we're trying to make. Less than or equal to, because obviously if I have 10p and I have a 10p coin available, I can take that 10p. So then we just calculate the minimum by doing this. Cool. So the minimum amount has either already been found, or we can take a coin. We're trying to solve a smaller problem, but we add one because we've just taken a coin. And that's it. That's literally it. We've just populated the solution array. And then all we have to do is a ternary statement to return the amount or -1. So we return DP amount. If it's not equal to 100, then we know that we've found the value. So we can return 100. If it is 100, then we have not succeeded, and we can just return -1. Then we can just submit. That's all. And great. So the time complexity of the problem, just to do a quick analysis of this, the time complexity, well, we're doing a outer loop, which would be if n was the amount, this would be O of s times n. No, not n is the amount. Let's say n is the coin length. Because n is a constant, the number of coins in our denomination, the time complexity will grow as we have more coins in our denomination. Obviously, this is also scaled by the outer loop, which goes up to the target. So S, in this case, also scales the time complexity. But this is much more reduced than doing the exponential way, which you would have had to do if you did it recursively. Our space complexity is O of S, because we're simply allocating an extra data structure with a size of S, the amount that we're looking for. So that's all.